Let's record. Okay. All right. So morning, everyone. So let's catch up with where we last left off previously. I do believe, okay, my memories will be right, that in our last lecture we managed to clear one of the examples associated with polar coordinates form of a certain potential flow theory. Okay. I believe I've cleared this. Okay, so now let's move on to, all right, something which is very, very close to the heart of potential flow. Okay, and in this case, we're talking about basic, all right, 2D potential flow entities. Okay, so just to recap, we've basically proved early on that stream functions are and velocity potential functions of potential flow entities are basically linear. And what it means that, okay, it is possible for us to get more complex flow fields, okay, by simply adding the stream function or the velocity potential function of one potential flow scenario or entity, all right, with another 2D potential flow entity. Okay, but before we do that, let's find out what sort of basic 2D potential flow entities are there out there for us to, do whatever that we want, add this and so on and so forth. Okay. Now, the first one will be uniform flow. Hopefully you guys can see my mouse over here. So let's say we have an XY coordinate system and we have a uniform flow that's moving from left to right, parallel to the x-axis. So if you think about it, surely, all right, the streamlines will be parallel to, all right, the uniform flow direction. And let's say this uniform flow has got a velocity, all right, magnitude of capital letter U or cap U. Okay, so the horizontal lines here will depict the streamlines. So we have psi 1, psi 2, and so on and so forth. Now, we all know the velocity potential lines must always be perpendicular to the streamlines. So the dashed lines here, okay, as indicated by phi 1 and phi 2, this will be the velocity potential lines. Okay, just so we're on the same page here. Now, so what happened is, if you think about it, okay, based on this scenario, okay, the only velocity component we're going to have will be the small u velocity component. That means, all right, the x direction velocity component. The velocity component along the y-axis, all right, must be equal to 0 then. So based on that velocity component information, we can essentially relate them to the stream function. So basically, we can express del psi by del y equals to cap u, all right, whereas del psi by del x is nothing but equals to 0 because, all right, the vertical velocity component is 0. Okay, I'm quite sure you guys know how to do partial integrations, all right, such that at the end of the day, all right, okay, by doing our observations and so on and so forth, we will be able to arrive at the stream function associated with an uniform flow, which is nothing but psi equals to cap u y. Okay, so what happened is as u increases, okay, psi increases then because, sorry, not u, sorry. As y increases, all right, the value of psi increases. Okay, so essentially means that all these horizontal lines, all right, will have a gradually changing, all right, stream function value. Okay, now how about velocity potential function then, right? We basically do the same thing, relate the velocity potential function with the velocity components, and we're going to have del phi by del x equals to cap u, del phi by del y equals to 0, do your partial integration, and based on the observation method, okay, we can get this expression phi equals to ux. Okay, that means that these vertical dashed lines here are going to have different values, okay, according to exactly where x location they are located at, right? Okay, now it is always possible for us to come up with stream functions, all right, as well as velocity potential functions for a uniform flow that's skewed at a certain angle with respect to the x-axis or the horizontal axis. Okay, of course, clearly in this line, in this case, these slanted lines here will be the stream lines because they must be parallel to the flow direction, and these dashed lines will be the velocity potential lines. Okay, without going through the derivations, you guys can actually do it by yourself, but without going through the derivations, okay, these are the stream functions and the velocity potential functions associated with any uniform flow, all right, inclined at some arbitrary angle relative to the horizontal axis. Someone, hang on. I believe Edwin raised a question. If the vertical no change, y isn't partial y was 0, but instead is partial x is 0. Sorry, I don't quite understand your question, Edwin. But did Barry answer your questions? I hope Barry answered your question. Okay. Sorry, I missed the. Has the thing been resolved? Have the question been resolved, please, Edwin? Oh no, I don't know what's happening. Okay, I'll come back to this. Okay. Call me off guard because I was like focusing on this thing. Okay. All right, don't worry. If you guys have got any issues, please cut them there. Okay, I'll come back to them. All right. Okay. Sometimes I'm just looking at this monitor. I got 4 monitors on my table, so sometimes I may miss out the thing. Okay. Let me just continue. Okay. Now the next 2D potential flow entity that we should be concerned ourselves with will be the source or sink potential flow entity. Okay, so what happens is, as the name implies, right, a source and a sink basically means that a flow, all right, a flow that will see fluid moving radially outwards from a point or moving radially inwards into a single point. So what happened is, okay, this figure hopefully will shed more light. Okay, so let's say once again we have the x-axis and the y-axis. So that's the single point, and the single, all right, where the single point is located at the origin, right? Now the blue lines here will be the flow in this case, right? Basically, this blue line shows that the flow are basically coming up from one single point and then basically spread outwards in a radial-like fashion. Okay, and they all have got the same radial velocity. The flow components are such that, all right, we only have radial velocity components. Okay, that means VR, V subscript R is not equal to 0. However, because the flow is actually moving radially upwards, that means the tangential velocity V theta must always be equal to 0. Now, so in this case, the blue lines will indicate the streamlines. And if you think about it, the velocity potential lines, okay, will be, all right, these dashed lines over here, because only when you have a dashed line, this circular dashed lines, will they always be perpendicular to the blue color streamlines. Okay, so just bear in mind of that. Okay, now source and sinks. All right, sources and sinks. All right, they have what we call strength. That means, you know, in some ways, all right, the strength in this case will be the flow that's coming out, that's pouring out from this single point or pouring into this single point. Okay, and depending on which textbooks that you guys are reading, sometimes they may be denoted as M, Q, or K. Over here, we use Q. Q in this case, you may take it as the 2D volume flow rate that's coming out from this point or going to that point. Okay, all right. I'm sorry if you guys keep hearing chimes, right, of emails coming into my mailbox. Okay, now, so think about it. Okay, if we take the circumference, let's say, as mapped out by this dashed line, and multiply by the velocity component in the radial directions VR, that means if we write 2 pi r times VR, if you think about it, this is nothing but, all right, equals to the 2D flow rate coming out from the source. In this case, how do I know it's a source? Because, all right, there's no negative sign here. Over here, if Q is positive, means flow is coming out from that point. If Q is negative, means flow is going into that point. Okay, so in this case, Q is positive, so we're talking about source. Okay, if you're talking about sink, you can just put a minus in front of the Q. Manipulate this expression a little bit, you're going to get an expression for VR, okay, which is the radial velocity coming up from this, originating from this single point. VR can be expressed as the strength of the source, okay, divided by 2 pi r. Always bear in mind the tangential velocity must always be equal to 0 for a source and a sink, because everything is radial only. Okay. Now the velocity potential, okay, as well as the stream function, okay, can now be derived because why? Because we already know the velocity. We already know the expressions for VR, and we know that V theta equals 0. So armed with the expressions of VR and V theta equals to 0, we can basically, all right, associate them with, let's say in this case, all right, the velocity potential function phi, okay, as del phi by del I equals to Q divided by 2 pi r, and we know that 1 over r del phi by del theta is actually equal to 0 because we can relate it to V theta. Again, do your partial integrations, all right, simplify by observation, and you will arrive at the stream function, sorry, the velocity potential function for a source. Okay, it's nothing but phi equals to q divided by 2 pi natural log of r, or ln r. We can do the same thing for the stream function. Of course, the functions here will be slightly different, right? So in this case, we're going to have 1 over r del psi by del theta equals to q divided by 2 pi r, okay, because we're relating this to vr, and del psi by del r equals to 0 because we're relating this function to v theta. Again, do your partial integrations, all right? Do your observation thing, all right? You're going to get this this stream function expression, psi equals to q divided by 2 pi theta. Okay, so the expressions are not are still quite straightforward. Okay, all right, because these are basic 2D flow entities. Okay. Okay, so now, so what if we have arrived at those expressions early on? What can we do with them? I think that's the question, isn't it? How do we apply this principle? Because it sounds so idealized, sounds so perfect, sounds so simple, right? Okay, but they are useful, right, for some simple calculations, some estimates of very, very simple flow fields, as the next example will show us. Okay, so now with reference to the figure here, we have got an inviscid incompressible fluid. Okay, and we're told that it is flowing through a wedge-shaped wall. So this is the wedge-shaped wall. So it's like flowing into this slice of pizza, right? Into this point. Okay, so it's flowing from here, all right, going into a point, and that point is actually located at the origin of this XY coordinate system. Okay, we're told that if the flow field can be described by a velocity potential function, all right, phi equals to -2 natural log r, and everything expressed in standard SI units, then determine the volumetric flow rate, all right, bracket, per unit width into the paper, that means the 2D flow rate then, okay, into the opening. Okay, so we are provided, all right, with the velocity potential function, okay, we're told the extent, the angular extent of the wedge, in this case is pi over 6, okay, and based on that, estimate, okay, based on potential flow theory, the 2D volume flow rate that's going, all right, from here, or as indicated by the solid arrows here, into this small little tiny opening, which we can assume to be a single point. Okay, so now recall from early on. Okay, all right, we can relate the radial velocity component VR, okay, with what? With the velocity potential function as what? Del phi by del r. Well, given phi, okay, so that means we can actually take this phi function, put it into here, do a partial differentiation, and we're going to get VR equals to -2 over r. Okay, and in this case, it shows us that, all right, VR is actually inversely proportional to R. Okay, now since we are assuming that this is a sink, all right, and the fluid flow basically has got only this radial velocity component, that means V theta equals 0, and we don't have to worry about V theta. Okay, so now to solve this question, let's consider this infinitesimally small arc element, okay, as indicated by this red arc here. Okay, the flow rate that's going into this wedge or this arc element, okay, going to here. All right, if you think about it, let's express it as del Q. All right, this tiny change in flow, volume flow, is nothing but VR, which is VR, the velocity of the fluid that's going through this arc length here, multiplied by what? The radius at this point, which is, let's say we can write it as capital letter R, all right, times delta theta by basically del theta. Del theta is the angular extent of this tiny little arc element. So think about it, right? R del theta is nothing but the arc length of this part here. VR multiplied by the arc length is nothing but just the 2D flow rate that's crossing the arc length, all right, the arc of this small little element. All right, and surely this must be equals to del Q. All right, but we're interested in finding out what's the flow rate throughout this whole pi over 6 arc. Okay, so if that's the case, that means we can take this expression, okay, and do an integration. So we can re-express, okay, to find out what's the total Q, that means the total 2D volume, 2D volumetric flow rate. Q is nothing but the integral of VR, R d theta with the limits of integration from 0 to pi over 6. Okay, R in this case, capital letter R. All right, well, because early on in this based on this figure, we're using capital letter R, but we can re-express it as normally as the small r. Okay, for general considerations. So if this is small letter r, that means R and R here will be cancelled off, and at the end of the day, all right, you're just integrating what, -2 d theta. Okay, all right, and I'm quite sure that's a simple enough integration. Okay, for you guys. So do your integration, you realize that Q is nothing but equals to minus pi over 3. And of course, you can take pi as what, 3.142, and then divide by 3, and you're gonna get an estimate of about what, minus 1.05 meters squared per second for the total volumetric flow rate. Okay, it's minus because it's going to a sink. Okay, clearly this is a sinker because fluid is moving into a point rather than moving out from a point. Okay. Okay. Now another. Okay, there are many. I'm not say many. There are a few. So there are like a few classical 2D potential flow entities, right? And we have covered source and sink. The next one is what we call a free vortex. A free vortex is nothing but a flow field whereby fluid is seen, or basically fluid is rotating about a point, a single point, in a very idealized manner. So basically, right. If we reference the figure over here, let's say once again we have an XY coordinate system, and let's say the fluid is spinning or rotating about the origin. So at the end of the day, that means the streamline, okay, can be represented by the blue circle over here. Okay, the blue circle over here, because the fluid just spins round and round. Okay, fluid just spinning round and round. Now, if the blue circles here are the streamlines, then clearly, right, the radar lines in this case will be the velocity potential lines. So we have a scenario whereby the situations, okay, are opposite to what we've seen for the source and sink. Remember, for the source and sink, the radar lines are the streamlines, all right, and the circular lines are the velocity potential lines. Whereas for a free vortex, okay, the radar line, not radar lines, sorry, the circular lines, okay, are actually the streamlines, and the radar lines are the velocity potential lines. Okay, it's a classical opposite thing, right? Okay. Now, please take note that if you consider the circulation around a fluid flow region with nothing inside, no free vortex, no source, no nothing, no uniform flow, okay? If you consider the circulation of this control area or control volume, okay, that's enclosed by an arbitrary loop, okay, you'll realize that circulation gamma is always equal to 0. However, if let's say this loop, okay, actually enclose a certain flow entity, let's say it's a source, it's a sink, it's a free vortex, circulation need not be 0. Okay, in fact, okay, for free vortex, okay, whereby the tangential velocity is defined as k over r, where k is the strength of the free vortex. Okay, the circulation around the circular path of its radius. That means if you calculate the circulation, all right, let's say around this circular loop, around this circular streamline that has got the center of the free vortex enclosed in there. All right, the circulation can be worked out to be equals to 2 pi k. Okay, so now before I go any further, all right, I think it should be clear that in this case, all right, the velocity components will be quite different from what we've seen from the source and the sink. Remember, for source and the sink, we only have radial velocity components, and tangential velocity v thetas are always equal to 0. So that's for the source and sink. For the free vortex, just like what's happening to the streamlines and the velocity potential lines, where everything sort of like flips on their head, right? So the velocity components here, right, also, will be quite different. So for a free vortex, clearly, because the fluid is only spinning around, in that case, VR must always be equal to 0, because there's no radial velocity component, because flow is not coming out from a point. Okay, in this case, the only non-zero velocity component will be the tangential velocity, because it's going around in a circle. Okay, all right, so we're talking about the tangential velocity along the circumference of the circular streamline. Okay, so, okay, let's come back to this. Let's derive some expressions. Okay, now early on, we have already shown that K, which is the strength of the free vortex, can be equals to, it's nothing but the circulation around this free vortex divided by 2 pi. Once we know this, and once we know, all right, v theta can be expressed as k over r, that means we can work out, okay, the velocity potential functions and the streamline function and the stream functions, all right, by relating the stream functions and the velocity potential functions with the velocity components v theta. All right, remember vi equals to 0. Okay, okay, you can't get nothing from vi equals to 0 if you try to relate the velocity potential functions or stream function. Okay. Okay, and it can be proved that, all right, once you arrive at these functions, okay, just to double check, you can actually, all right, basically, all right, try to work out v theta by doing partial differentiations, all right, and you're going to get v theta equals to k over r. Okay, okay, so all these are just expressions that, you know, allow you guys to relate, okay, the velocity components with the stream functions and velocity potential functions. No big deal, right? Okay, but I think what's the big deal here is, do you see what's happening here? Okay, v theta, all right, okay, is nothing but equals to a constant, because the strength has got to be constant, divided by r. V theta is inversely proportional to r. So think about it. That means as r becomes greater and greater, v theta tends towards 0. Okay, that's fair enough. All right, because we are saying that, right, as r tends towards infinity, that means as one goes further and further away from a free vortex, okay, we're going to feel less and less, all right, effects of the vortex, which is fair enough, because a tornado that's happening in the Pacific Ocean, I don't think we can really feel it here, right? Okay, maybe we're going to get slight gusts, more rain, but by and large, we don't really quite feel it per se. It's so far away. However, okay, if we go the other way, as r tends towards 0, then we have a problem, because v theta will then tends towards infinity. Now, that's not very realistic and goes and basically goes against what we actually encounter in real life. Okay, so this can't be the case for real fluids. Okay, because real fluids, okay, has got viscosity, right? Non-zero viscosity. Non-zero viscosity essentially means that due to viscous effects, velocity can't reach infinity, because it doesn't make sense at all. Okay, so what happened is, okay, let me introduce another vortex called a force vortex. Okay, unlike a free vortex, which is the potential flow entity, a force vortex is not a potential flow entity. Okay, all right. Okay, so what happened is, okay, if you have a free vortex that's spinning, and let's say I've got two pieces of stick that's arranged 90 degrees, right, as shown in A, okay, due to the deformation within the flow here, okay, these two sticks will start to deform, all right, and they will undergo angular deformations. But because it's a potential flow, so what's going to happen is, all right, okay, vorticity will have to be equal to 0. All right, that means that any angular deformation in both directions will have to cancel out each other, such that, right, vorticity equals to 0 and it remains an irrotational flow. However, for a force vortex, if you put across here, that's two sticks, that's about, you know, the cantilever about its midpoint, you realize that the net deformations, okay, will not be equal to 0, because a force vortex is not an irrotational flow. Okay, a force vortex is what we get when we have a real life vortex, okay, whereby velocity actually varies from 0, from the center of the vortex, to basically to a certain tangential velocity, okay, which is dependent upon, all right, just how far you are away from the center of the force vortex. A free vortex, all right, the variation, the velocity variation of a free vortex, right, in the center of the free vortex actually goes this way. For force vortex, actually it goes this way. Imagine it's like a solid cylinder that's rotating. Okay, surely the tangential velocity will basically go higher and higher. All right, the further away you get from the center of the rotating cylinder. And real life vortices actually, all right, takes upon aspects of both a free vortex and a force vortex. How so? So what happened is, of course, this is a very simple schematic, but this by and large shows what we see in real world vortices. Okay, so let's say this is the center of the vortex. okay, and R basically is the distance away from the center of the vortex. Let's say a tornado or a hurricane, okay. The vertical velocity, the vertical axis over here shows the velocity, right, the tangential velocity of this of a real life tornado, let's say. So what happened is, if you measure the velocity of the tornado or hurricane, okay, is very close to zero. And what happened is, very close to the center of the tornado, all right, it actually behaves like a false vortex, and the velocity actually increases, right, more or less linearly, okay, up to a certain velocity, maximum velocity. And that's where, all right, the false vortex behavior, all right, basically gets replaced by the behavior of a free vortex. So, all right, after this critical radius, okay, and after that, what we will see is that the velocity, the maximum velocity, suddenly will undergo some very, very drastic reductions this way. So as you can see, right, the inner region of a tornado behaves like a false vortex, but the outer region, right, of the tornado behaves like a free vortex. Right? So one false vortex here and one free vortex here. So it's actually a combination of two different vortex behavior. Okay, all right, because why? Because of viscous effects. All right. Okay, so now with that, let's move on to an example. A very simple one. Okay, don't be too worried by the by this figure here. Okay, it just looks horrible, but actually it's not that bad. Okay, let's go through this quickly just to get some understanding. Yeah. Okay. Now we have liquid. Okay, that's draining from an infinitely large tank, as shown by the figure here, through a tiny little opening. So imagine this is a cross section of a superbly large tank. And water, you can say it's water, right? Okay, liquid is actually flowing through this tiny little opening here. Okay, so what happened is, all right, as liquid is going through this hole, all right, it will form a spiraling vortex. Okay, whereby the velocity of the vortex is a function of distance away from the opening. Okay, and in this case, we're to treat that the velocity of this vortex here, all right, represents that of a free vortex, having a velocity potential function of phi equals to gamma divided by 2 pi theta. So given this, all right, and with reference to the figure here, determine an expression relating the surface shape. That means this surface shape, right, an expression for the variations in the what do you call it, in the parabolic shape, if you will. Okay, all right, relative to the vortex strength gamma, because as the vortex becomes weaker or stronger, surely, right, this parabolic like shape, right, is going to change. All right. So how to go about solving this? Okay. So what happened is, since we are asked to work out the shape of the surface, of course, this is highly exaggerated. Huh? Okay. All right. It's not going to be that. It's not going to look like a bloody black hole. Right? All right. It's not like the event horizon. Yeah. Okay. So now, since we're asked to work out the shape or the profile of the surface. Okay. Let's focus on the one particular streamline, as indicated by the red dash line here. We just focus on that streamline that describes, all right, this surface line, if you will. Okay. So now, since we are focusing on a particular streamline, what should come to our mind right away? Bernoulli's equation. All right, because Bernoulli's equation is applicable along the same streamline. Okay. Now, how do you write Bernoulli's equation? Assuming no losses, no nothing, because, all right, well, no information about losses are actually given. And because this potential flow as well, there's no viscosity, because we assume viscosity is 0, so there's no viscous losses. So let's just say no losses. Okay, because the question does not provide any information at all. So if that's the case, all right, so let's say the red dash line can be we're applying Bernoulli's equation along this red dash line. And let's say that we consider one point here, which is far away from the opening and along the surface of the water. And point 2 can be any point, all right, along this slope here. Okay. So based on Bernoulli's equation, all right, if we do an energy balance, all right, we can write P1 divided by rho g. Okay, that means static pressure at point 1 plus v1 squared divided by 2g. v1 will be the velocity along the surface plus z1. z1 will be the height at point 1. We set it equals to P2 divided by rho g. P2 will be the static pressure at any point here. Let's just say it's here. Plus V2 squared divided by 2g. V2 will be the velocity at this point, some arbitrary point here. Plus Z2. Z2 will be the distance relative to Z1. Okay. So now, okay, the questions did not provide us with a lot of information, but there are some key assumptions that we can make based on what we're given. First thing first, we're told that the pressure acting along the surface here, along the reservoir, the surface of the reservoir, and because it's basically we're told that it's an infinitely large tank. So the pressure that's exposed to the ambient surely must be atmospheric pressure. So P1, okay, we can assume the pressure to be the same as the atmospheric pressure. Okay, so P1 here is basically atmospheric pressure. In fact, it's the same for the pressure at point 2, because think about it, all right, it's actually facing the ambient condition along the surface, right? Because it's along the surface, it's not here, it's not there, it's right along the surface here. So the pressure that's experienced by point 2 is actually P atmosphere as well. V1, that means the velocity here, okay, at some point that's far away from the opening. So it's an infinitely large tank. Imagine it has the size of the ocean. All right, so V1 can be, we can assume V.
Prof, you are muted, Prof. Prof, you're muted, Prof.
Hi, for how long have I been muted? Oh no, is it just for like 1 minute? Okay.
Yeah.
Who muted me? Who muted me? Oh no. Did anyone mute me? Okay. Anyway, where's the last time? Where did I last stop? Is it here? Oh no, Melvin, did you mute me? Atmospheric pressure. Oh, the assumptions, you mean? Yeah. Okay. Okay, sorry about that. Yeah, I don't know why, for some reason, people can mute me even though I'm the host of this thing. I'm not too sure why. Does anyone know why? Okay, stop muting me, people. Just like, stop trying to record the video on your own. Okay. All right, please don't mute me. I don't think I click on the mute button myself. Okay, let's go back. Don't worry. Okay, we didn't lose too much, about 1 minute. Okay, I believe, why don't I just recap a little bit? So we are basically trying to apply Bernoulli's equation, right, between points 1 and 2 along this line, this surface. And let's say that this surface can be represented by, we assume that this surface basically can be represented by a streamline that's connecting these points 1 and 2. Okay, so now, because of this unique condition, unique situation, we can make some assumptions to simplify the Bernoulli's equation. Okay, so at point 1, if you think about it, this is an infinitely large tank. Okay, so at point 1, all right, we can say that, all right, it's so far away from the opening, it's so far away from this vortex that it does, right, that it's not going to be affected by the presence of this vortex. All right, so in this case, we can say that P1, right, can be assumed to be what? To be atmospheric pressure because it's exposed to the atmosphere or the ambient conditions. The same goes for P2. All right, because we're not talking about, we're not referring to a point within the reservoir or within the large tank here, within the volume of water there. Okay, P2, 2.2 is actually a point along the surface, which is exposed to the atmospheric condition as well. So P2, all right, just like P1, can be set to P atmosphere. Okay, V1 can be approximated equal to 0. That means the velocity at point 1, all right, we can assume it to be 0 because it's so far away from the vortex that the presence of the vortex does not have any appreciable influence. It's not going to drag the velocity around the opening such that velocity at 1, all right, has got a significant value. significant velocity value. Okay, so let's say that point Y is so far away. Okay, the velocity, all right, is approximately equal to 0. Z1, we just set it as a reference height. Okay, we just set it, that means we can just set it to 0. Okay, now how about V2 and Z2? V2, think about it, V2, we're supposed to assume that the velocity variation follows that of a free vortex, all right, and defined by this velocity potential. So V2 then is nothing but V theta, the tangential velocity of this free vortex. Okay, and V theta, as we know, all right, is nothing but gamma divided by 2 pi r. All right, we can figure this one out from here. Okay, all right, do the partial differentiation if necessary. Okay, Z2, all right, the height here, we just say that, look, it's at some height, ZS, let's say. Okay, all right. So now with all these assumptions, okay, which will allow us to simplify this expression, let's see what we get. Okay, so this is just copy and paste from previous page. I just want to put it up there so that everyone can be reminded of the assumptions that we made. So plug in the stuff in here. All right, so P1 is P atmosphere divided by rho G, all right, plus what? Velocity V1 term here is 0, so all goes to 0. It's actually here. Why did I flip to the previous slide? All right, so over here is the V1 squared divided by rho G term. Okay, is it rho G? 2G, sorry. Okay, and it goes to 0. All right, Z1, we set it to 0. On the right-hand side of the Bernoulli's equation, P2 is P atmosphere as well. V2, in this case, is actually this one. So we plug gamma divided by 2 pi r as V2 here, squared divided by 2G plus ZS. So simplify, cancel off the terms that you need to cancel. Eventually, you're going to get an expression ZS equals to minus gamma squared divided by 8 pi square r squared G. Okay, and this will be the, all right, the expression that relates the surface shape to the vortex strength gamma. Okay, right, the surface shape being defined by the variation in ZS. Okay, so this will be the answer, but I think what really matters is not getting this at all, but is to appreciate the fact that gamma is a constant, okay, pi is a constant, G is a constant. So that means effectively ZS is indirectly proportional to R squared. And that means that, well, if it's R squared, that means the shape of this surface, of the free surface here, okay, basically, all right, takes on this parabolic shape. Okay, and if you think about it, right, even though this is based on inviscid flow, because potential flow theory assumes 0 viscosity, okay, this profile here actually gives a very reasonable estimate of, all right, of the change in the height, actually. All right, so you guys might want to do this simple experiment next time, go to the basin or whatever, you know, put the plug in, fill up with some water, put the plug out, and see the spiraling vortex. Okay, all right, and observe the shape of the free surface, all right, okay, as the fluid moves towards the center of the opening. Okay, you realize that actually, all right, it looks sort of like a parabolic shape, not exactly, you know, R squared, but close enough. Okay, because we still have to be mindful, right? Okay, real world fluids has got non-zero viscosity, whereas potential flow assumes 0 viscosity. Okay, now. Now that we've seen these few 2D potential flow entities, that means we are now able to combine them to form more interesting flows, thankfully. Okay, because a uniform flow, sourcing, they're not that interesting. Okay, let's try to combine them. And one of the first so-called combined flow that we can get is actually a doublet. Okay, a doublet, as you can see from the figure here, can be formed by adding a source on the left-hand side of the y-axis with a sink on the right-hand side of the y-axis, okay? And they are located in such a way that their distance from the origin basically is the same. So source is located at distance A from the origin. Sink here is located at the same distance away from the origin, A as well, okay? So a doublet is actually formed by, like I said, a summation of a source, a combination of a source and a sink. Now, remember what we say about stream functions and velocity potential functions? They are linear functions. So the combined stream function for this flow here, this is psi, is nothing but the stream function of the sink plus the stream function of the source. And if you do that, this is what you get. Okay, this is what you get. Okay, now the goal of adding them up, all right, and trying to derive some sort of equation here is to find out this combined equation that will allow us to find out the velocity components and the stream function values, or the velocity potential function values for any arbitrary point around this, all right, that resides in this Cartesian coordinate. Let's say the arbitrary point is P. We want to get an expression for P with respect to R, okay, where R is the distance from the origin to this arbitrary point P. And this R here is actually inclined, it's basically at some angle as well from the x-axis. Remember, for the source and the sink, they have their respective theta. So the sink will have this theta 1 and theta 2 with respect to this arbitrary point P. They also have R1 and R2 here. So the key now is to combine them. That means instead of expressing them as R1 and theta 1, we want to manipulate the expression so that we get a single function, not say single function, the stream functions and the velocity potential functions in terms of R and theta. Not R1 and R2 and theta 1 and theta 2. No, just R and theta. Okay, now how do we do that? Okay, I'm not going to go through in detail, but I think you guys should roughly know how we did it. So we start off from this. Okay, as I said, we can just add the stream function of the source and the sink together, and this is what we get. Once we have got this, let's take tangent on both sides. Okay, after we move the coefficients, all right, minus q divided by 2 pi to the left. Okay, all right, once we've done that, then we take tangent, okay, on both sides. So we're going to end up with tangent of minus 2 pi psi divided by q equals to tangent of theta 1 minus theta 2. I'm quite sure you guys have seen this before. Okay, I believe this is something that A-level had taught us. Okay, expand this thing out. We're going to have tangent theta 1 minus tangent theta 2 divided by 1 plus tangent theta 1, tangent theta 2. Okay, so now, how can we make use of this expression to convert our theta 1 and theta 2, R1, R2 into R and theta only? Okay, let's go back to the figure here. What's tangent theta 1? Tangent theta 1, where's theta 1? This is theta 1. Okay, if you want to take tangent theta 1, it's nothing but the opposite, that means the vertical length here, divided by the horizontal length here. Opposite divided by adjacent, right? Now, what's opposite? The length of opposite. Opposite is nothing but, right, R sine this theta. Okay, so you resolve it vertically. So opposite length will be R sine theta. How about the horizontal length or the adjacent? If you think about it, it's nothing but R cos theta, okay, minus A, which will leave us this bit, which will be the adjacent, right, if we were to take tangent theta 1. Okay, and we're going to get this expression for tangent theta 2. Rinse and repeat for what? Tangent theta 2. Basically, use the same technique. We're going to get R sine theta divided by R cosine theta plus alpha, plus A, sorry. Okay, take this tangent theta 1, tangent theta 2, plug it in there, simplify, you're going to get this. Tangent of minus 2 pi phi psi divided by q equals to 2ar sine theta divided by r squared minus a squared. Okay, let's take inverse tangent and then move the coefficients over there such that at the end of the day, this is what we get. We're going to get psi, all right, equals to minus q divided by 2 pi inverse tangent of 2ar sine theta divided by r squared minus a squared. Assume very, very small angles, then we can get rid of inverse tangent. And this is what we get, minus QAR sine theta divided by pi into r squared minus a squared. Okay, now let's assume that the value of QA divided by pi is a constant. Okay, and that, all right, we assume the scenario whereby as r tends towards 0, okay, hang on. Yeah, so basically we assume that Q times A divided by pi is a constant. Okay, doesn't matter how the value varies. And in this case, actually, all right, we're assuming that actually the arrows move a little bit. I'm not too sure. So actually, this shouldn't be R. Okay, it should be as A tends towards 0, Q tends towards infinity. Okay, but as A tends to 0, what's the implication? The implication, right, is that the source and the sink are gradually moving towards the origin. Okay, it's gradually moving towards the origin. Okay, and as they do so, Q increases such that the product of Q and A remains a constant still. Okay, so of course, it's not realistic, but it's a hypothetical scenario. Okay, all right. Of course, there are people who say that, look, how can you have a source and sink eventually meeting origin? You can't. Okay, but for the sake of mathematics, this is what we assume. Yeah. Okay. Okay. Now, since QA is a constant, that means we can assume that K equals to QA divided by pi. All right, is a constant, and let's define it as the doublet strength. Okay, then we can simplify the combined string function psi as this, minus KR divided by R squared minus A squared sine theta. Okay. Now, since we already assumed previously that the source and the sink approaches each other such that they will eventually coincide at the origin. So if that's the case, as A tends towards 0, the R divided by R squared minus A squared actually tends towards 1 divided by R. And that means we can further simplify the string function, right, such that we get psi equals to minus K sine theta divided by R. And we can rinse and repeat and get basically, all right, a sort of like a similar type of expression for the velocity potential. Phi equals to K cosine theta divided by R. Okay. Now, this part here, you guys just have to get an overall general understanding. I think that's fine. It's not the most important. What's important are these combined functions. Okay. I'm quite sure that, you guys would can guess that, right? The function here looks rather funky, right? Okay, if we plot out the streamlines based on using this string function, well, you're going to get something very, very interesting. In fact, if you do it, you're going to get something like this. It doesn't look like a source. There's no source in there now. There's no sink in there now. In fact, you don't see any source and sink arrow. In fact, all right, you're going to have two sort of like spiraling things, right? One above the x-axis, one below the x-axis. Okay, and this is how a doublet will look like. Okay, now a lot of people will probably say that, look, this doesn't resemble anything in real life. Okay, but it does resemble a little bit. Okay, all right, like a vortex ring. Okay, a vortex ring. Remember, a circular vortex ring sort of like going spiral this way as it moves. It does resemble a vortex ring that's moving through air or fluid. Of course, it doesn't look exactly like a vortex ring, but it is close enough. Okay, simply because the differences were due to the viscosity differences. Okay, potential flow assumes 0 viscosity, real world has got non-zero viscosity. Okay, now of course, it doesn't really reflect real world scenarios, but at least mathematically speaking, it allows us to explain very, very simple fluid flow behavior. Okay, remember, potential flow theory is a very old theory. Back then, people didn't know that there's such a thing called viscosity, and this was the best they've got. Okay. All right. Okay. I'll tell you what, let's go for a break, and then we'll come back and continue, all right, with other forms of combined flow, all right, where we'll look at source in a uniform flow and then a doublet in uniform flow. Okay. I don't think I want to rush this because potential flow theory is actually a very heavy topic. Okay. All right. So, yep, please go for a break. Go for a break, stretch your legs, wash your face, and we'll come back, let's say about 10, 15 minutes time. Okay. All right. I'll stop the recording now. I'll see you guys back soon. Hang on. Let me stop the recording.